Well, I am Adam. This is Frederick. um, so, like MR said, we started this class 6 years ago, but in our first year, both of us had just started. And we wrote a proposal to do the first 3 years in California, and then we took a year off, and we did the next 3 years in Cyprus, which we'll tell you about a little more. The class meets just once a week on Thursday, and for 3 hours. We usually spend the first half in lecture and discussion, and the second half doing basically labs. So not necessarily pipetting at a lab bench, but working through various softwares and techniques that we'll describe shortly. We also offer a lunch on Mondays, basically helping students with MATLAB and LaTeX and whatever problems they're working with. And in this case, you can see we're also offering peer review or reviews basically of rough drafts. So one of the major focuses of this class is science writing. So the ultimate underlying theme of this class is hypothesis-driven research. So the class is about doing research, having students as freshmen doing research. And if you made one statement, I would say it's very difficult to turn observations of the natural world, which is very complicated, into numerical data that can be analyzed quantitatively. It's not quite as hard, perhaps, if you design a very controlled experiment for the lab, but actually observing things outside and turning it into something you can do something with is very hard. So there's a picture of Leah making observations in a tomb carved out of Aeolian sandstone on the west coast of Cyprus. She turns that into field drawings describing the orientation of these different cross strata, some kind of numerical analyses, in this case in MATLAB, then turned it into a rose diagram describing the direction that the wind flowed 10,000 years ago. So this is just one example, and this is ultimately the theme that we try to recover in virtually every aspect of this class.
So we'll give you some examples of the product of our class, the so-called deliverable, if you will. What are the students ultimately able to do after spending these 12 weeks with us, and various others in the classroom and then in the field? And the answer is a whole lot. So we went to Cyprus. This is Cyprus and its location. And just a handful of examples of maps made by the students. This one is ultimately where we went in a number of years. The codes here, BD7, EG1, EF2, are showing areas labeled by the archaeologist, and then the smaller units there, labeled Petrorades, Peristeres, are areas where we did some very detailed investigation. So all of this is geo-referenced. This is a map produced in the Geographical Information System, ArcGIS. People went there, as we will show you, with handheld instruments to get very accurate locations. So first question is, where are you? Well, this is where we were. They did, as Adam was saying, translate some of these non-necessarily numerical observations into numerical data. This is a map of the relative occurrence of the variety of man-made objects that were found on a controlled grid in an agricultural field. So this is essentially the stuff that prior civilizations left behind: pottery, kitchenware, storage vessels, and so on, which then lends itself to analysis. This is a third example. This is a map it's a combined map. The large color variations here are what the Earth's total magnetic field variations are as we walked around with the detectors near the surface. And the various areas that are colored are anomalies in the magnetic field, which are indicative of things that are unusually magnetic. This could be baked bricks, this could be metal, this could be subsurface structures. And so you'll see labeled the various techniques that we use. ERT is an electrical resistivity, which is an active measurement. GPR is ground penetrating radar, which is another active measurement. We'll talk a little bit about these. And then magnetometry is the passive measurement that just sort of walks with the detector over the surface and sees, well, what is the magnetic field? And then underlying there, the black pebble-looking things are actual structures that the archaeologists had prior to our arrival there, already dug up. So we were right next to an active excavation. We're just in an area where we didn't know what else would be there. That's 30 years. The drawings are 30 years of excavation. We're trying to cover an equivalent area of field for potential excavation in the course of a week, let's say. Here's one last map, is an air photo now integrated and geo-referenced with these maps right on top of a particular area. And so by going there year after year, we always went to new sites. We never knew what we would find. Some years worked a lot better than others because the equipment, comes and goes in terms of performance and students' capabilities and our experience. And so every year it was new for us and it was new for the students. This last year was particularly successful. Here what you're seeing, these areas, the lines meeting at right angles that I hope you are all seeing, and then that wedged structure there in that lowermost map here. This is a ground penetrating radar map. And if there's any evidence for a buried man-made structure underground, it would be, well, something linear, something meeting at right angles, something that in other words really looks like a structure, like a chapel, a sanctuary, a basilica that have been found nearby. And this was one of the very successful detections using this active radar measurement. And then once again, a lot of the emphasis was on data integration. We went repeatedly over these fields with different techniques, and here there's also electrical resistivity, the survey area marked here. All of these maps here, these last 4 or 5, were made by our very capable students. So here are the structures that I was talking about, outlined by those very students to show you what potentially and most likely is evidence for more archaeological remains.
So, well, just to highlight one very important point that Frederik made is that to make this class exciting for us and hopefully more exciting for the students, we had to go to different places every time. That's the point, is that if we were basically recovering the same result over and over, we would lose our excitement, and I think it'd be a lot harder to make the students excited. The students like it when they see us not being able to figure stuff out. Anyways, the second deliverable slash product of this class, so what we just described is the field project. We'll show you how we get to the students to the point where they can generate that kind of result from a field product, but we're also at the same time teaching them to write about their research. And to do so, they have to do so independently rather than as a group. The field projects are done as a group. And so throughout the class, there are actually 3 writing assignments, and they also involve original research. So these are not book reports, they are not literature reviews, they are students finding data that is numerical or data they can turn into numbers and then analyzing it. So here are some examples of research papers. I'm mostly going to show you figures from them. It's not that fun to just read papers on the screen. But here is an example of a student who was looking at the distribution of lead deposits in England and the distribution of Roman mines, essentially the infiltration of the Roman civilization into the United Kingdom. And what you can see is there's this black line called Hadrian's Wall that the Romans didn't seem to go beyond, despite the fact that there are lead deposits to the north. So the student's hypothesis or question is, what stopped the Romans? And they went through and, in this case, collected temperature anomaly data from various proxies, things like tree rings and ice cores and whatnot, put it all together and plotted it as a temperature anomaly compared to today through time, and then highlighted the timing of attempted Roman invasion. And then what they tried to do was compare, sorry for the resolution here, based on that data and a modern climatology, so data from modern weather stations, how many days are below freezing north and south of that wall. And what they found essentially is that as soon as you start getting north of that wall, the weather deteriorates. And maybe the Romans were kind of wimps. They didn't like the cold weather. It also turned out she did a similar analysis of topography and found that the surface roughness drastically increases when you move into Scotland, making it harder to build roads and thus penetrate. Another example here, this student was trying to evaluate why the Peshawar Valley, which is basically the border between India and Pakistan, this very important pass through these mountains, was settled by the Greeks. Alexander the Great had traveled across all of Persia and basically made it that far, and there's a continued Greek settlement in that part of the world, which is a little bit crazy. And so here she compares mean temperature, the upper plot mean temperature to total rainfall, again derived from weather stations from all these different towns, coded here in the legend, and then also compares mean temperature to elevation. And what she noted was that Peshawar, the red circle, seems to be an outlier. All the rest of these cities seem to group, or basins seem to group in a certain area, and Peshawar is different. And then these complicated set of horizontal and vertical lines outline the optimal ranges for growing wheat and barley in terms of temperature and rainfall. And so you can see, or basically she argued that Peshawar was closer to optimum for the growth and unique compared to these other places, and that's why they settled there. Just a couple other examples. In this, the student asked the question, this is Ethiopia. You see the town of Aksum, which was the center of a major population that basically controlled trade in this region for hundreds of years. But there was a very interesting, essentially, diaspora where people left Aksum and moved south to Lalibela, and the entire region lost power. And he asked the question, why? In this case, there were no climate records from Ethiopia. So he had to go to Uganda, where there is a lake that contains sediments that record climate. So he compared on the left, sorry, the resolution is not translated well here, but he compares the climate in Ethiopia to the climate of Uganda for the last 100 years to demonstrate that they are correlated. And then assumes that they have remained correlated and uses the Ugandan climate record to infer whether there had been a climate change in the ancient past that may have affected the civilization of Aksum. When he did so, he found, lo and behold, there was a significant drought that would have led to soil deterioration, and went on. And he also described the mean roughness and how the soils would have deteriorated for a given size of drought based on modern parameters applied to the ancient past, and came up with a coherent story. Just one last example. In this, it's actually back to that one of the papers we already described. The student tried to figure out why Alexander the Great would have followed the path he did from Greece across Persia and eventually into the Peshawar Valley, which is near where that purple dot is up in the upper right. And they essentially, in MATLAB here, generated elevation profiles along, in this case, the black line is Alexander's path, and then a whole bunch of other lines that actually would have been straighter as the crow flies. But it turned out, not surprisingly, that Alexander and his crew found essentially the path of least resistance, or the least roughness, and so on. So these are examples of student products at the end of the class. This is what we hope that they can achieve, both in terms of field research and collecting their own data, and in terms of data mining and turning them into true quantitative analyses and conclusions. So now we're going to tell you how we give them the tools to get to that point.
Okay, so what are some of those tools? And the words have been mentioned in this venue before, no doubt. One of them, this is how we write what we write, is called LaTeX or LaTeX or latex, but don't Google that. What is it? Well, it's a text-based typesetting tool. This is very important that it's text-based, which means if you've written a whole book of 1,000 pages, that it will still create a very, very light file, because all it's storing is your text, not complicated other things like most commercial softwares do. It was written by a single person, by hand, in the 70s. At this point, I think he's still alive, and he offered people $2 for every bug, and then kept doubling it. And I think the price on finding a bug is now something like $128,000 that you could get, because it's completely free of bugs. People never cashed it. Yeah, people didn't. Some of them didn't cash those checks because, like, finding a bug in LaTeX, even though it was only like $256, would be like a frameable thing signed by Donald. That's how perfect it is. Okay, it's free because it was written by a bearded man in the 70s, but it has many higher level distributions. We teach students how to use one or two various packages that will help you use LaTeX, but the underlying engine is a very light piece of code that you run in any editor you want. People have been writing thousands of packages for it to do posters, to do presentations, to do things that look like PowerPoint, to write entire books. Every scientific journal that deals in sort of natural sciences or mathematical sciences has a package for their style. So if you've written a paper for the Journal of Geophysical Research and it gets rejected from it because while it's still very good, it doesn't fit in the journal, then by changing the package name, you will typically completely reformat it in a matter of a second to the Geophysical Journal International, which requires different reference style, different table abbreviations, different equation styles, and the packages are just existing for your thesis, your junior paper, your journals that you're working in. What is really good is it excels at relative referencing. If you put a reference label somewhere on some page to some table, then you can say, hey, remember that label which I called label? I can now 50 pages later say, hey, that's on page ref, and that was table ref of that label, and you can relatively reference everything. So if you switch 2 chapters and you have a 1,000-page book, you don't need to go through and renumber everything because it keeps track of where you are at. Does that for chapters, reference tables, or things you make up. The number of times you say the word bingo, you can add a counter that every time it updates it and say, I'm at 32 now. It pretty much is the de facto standard for mathematical equations. However, it's not meant for mathematics. It originated there, but lots of people in the humanities are writing it because it affords all of this beautiful text control. It's also very much smarter than what you can buy commercially because it was really written with beauty of the page in mind. Well, what's MATLAB? MATLAB is a scripting language. In terms of coding, people talk about C and Fortran very much, and Java. MATLAB is one of those languages that's actually written in another language, and if you type a line, it will do something. You don't have to have a compiler. It's not really machine dependent. It's a very light piece of code originally. I'm going to go back there. It was originally written by a single person, Cleve Moeller, who wanted to do certain things. In fact, what he wanted to do was compute that logo, which is it's a wave in a membrane on a square domain that's pegged in 1/4 of it in the corner. So that thing that you're seeing that's stuck there is a boundary condition, and the rest of it is a flapping, loose end wave through such a membrane. And this is one of the only, it's an example of a very simple geometric domain on which there's no analytical solutions for the wave equation. And he's like, well, I got to compute this. And he made his software to be able to do it. It's expensive, but we have it. Also, cheap knockoffs exist, and we are using it because we have it. If you learn to program in it and you want to switch to another one, chances are you'll be doing well. It's sort of a gateway program. I still use it for higher level research, but it's a good entry for people who want to start. It is really good at matrix vector manipulation, which means it's actually, and that's what the name implies, mat is for matrix. So if you're doing high-level mathematics, you can actually get a lot of benefit by knowing what it likes, and you can turn that into some very, very professional-grade code. At the same time, it's very easy to learn, and so it has become by itself also a standard for educational computing in many, many departments. It has competitors. It works very well. GIS?
Yeah, so another software that we teach in this class is, the class of software is called GIS, Geographic Information Systems. Basically, the underlying theme of this is that every data point of any kind has an X, Y, and Z coordinate that is in geographic space, rather than random Cartesian coordinates. And so a latitude, longitude, or UTM coordinate type thing. And you analyze your data in that context. So it excels at understanding, for example, in this upper graph, the distribution of elevations in latitude and longitude. With respect to, again, here's Alexander's path and various other things. Another thing that it affords fairly easily is, for example, in the bottom graph, you can draw polygons representing some feature, in this case a geologic feature. It could be a human feature like the boundaries of a city, and quickly compute anything from layers above and below. So in this case, the average elevation in each one of those polygons. So these are computations you can do in MATLAB as well. In fact, a lot of this visualization could be accomplished in MATLAB. But it's this group of stuff to do is basically a little easier in ArcGIS. There are also, so this is ArcGIS, which is also incredibly expensive and quite clunky. It only runs on PCs. It has a rapidly advancing competitor called QGIS, which is almost ready for us to switch to, which is not platform dependent and free. But it's buggy and not quite ready. So I hope it will be ready soon. And the great thing with GIS on our campus, unlike MATLAB and LaTeX, is that there is a support system. There are a number of devoted GIS experts, Bill Gutta, Wang Yao, over in the GIS library, and they are very helpful to students. They also help us with installations, and it works out really well. One other that we've just started experimenting with is Google SketchUp. And so we just started this year. We were confronted with this geometric problem that the scale was smaller than can be achieved with ArcGIS. We needed to have a map, a 3D model of these tombs in which they were measuring these tilted beds that you can see. And so some SketchUp output looks like this. They basically measured lengths and angles of every wall of every tomb, and then on those walls drew lines representing the strata. And there's just a symbol up. So it's basically architectural software light. It's easy to use, immediately transferable to both ArcGIS and Google Earth, and free.
Okay, so how to do it, how to teach these softwares. All of them have a threshold. You know, you go like, oh, I need to learn all this stuff. Well, the best way is by example. And so the way we, over time, developed the requirement to do everything in LaTeX and MATLAB and be able to use ArcGIS is by giving people a small recipe to start from. So I'm going to give you my own little recipe that I made this morning for, this is a little LaTeX document, okay? It starts by a little class. It's going to be an article. You identify an author. You say begin document and end document. And you do /section. It's going to be section. /label is I have an intro that's going to be my relative reference. Then you'll say, you know, something. Hello, everyone. This is section. It's going to be the reference located on this page. This is how you spell my name correctly. Here's Euler's famous formula. You begin equation. You give that equation a label for future reference. You end it. As you can see, in that equation, Euler was no fool, though he was no fool. Okay, so that's 15 lines of text with, you know, a few extra slashes in it that once you run it once or twice through the LaTeX engine, it'll produce this document either in DVI or PostScript or PDF straight. It's going to have that title, it's going to have my author name, it's going to have the introduction, and, you know, this is section 1 located on page 1. This is the formula 1. But if that is somewhere on page 3,000 of your 3 million page, you know, great American novel, it will keep all these relative things. So it's very handy also for people. I'm not putting any footnotes, I'm not putting any references, but all of those are accomplished using the same set of tools where you call a label for a certain thing. Well, MATLAB, we give them a lot of references. I just Googled Euler's identity on the Wikipedia, and I found this little animation that says, you know, hey, and if you're no mathematician, this is about how something as n grows ends up on a circle, and Euler's formula will peg this point at -1. Okay, and as n goes to infinity, this is a circle, and that is 1. So I thought, all right, well, somebody did this in Java. So I had about, 10 minutes to redo it, and this is how you would write it in MATLAB. N equals 1 through 30, a little for loop, like in any language, a for each, a little loop of something. You say A equals 1 plus I pi. You read the index of the n, you raise to a power, you make a plot, you set the labels, you set the axis title, you set the range of things. And most of this is markup. The only piece of code that's actually in there is 4 indexes from 1 through n. Calculate something, that the line that says A equals, that's actually calculating, and the rest is some things you need to look up and how to plot, set various properties, the axes, and so on. And then at the very bottom, you can actually call LaTeX from within it to annotate your plots. So that little 10-line script produces this plot. That was the end of, I kept it going through 30. So if you execute my little recipe, you'll see a sort of a movie of it, and then it has that little label up on the top. And so we give students little things to do. Make a graph of this, collect some GPS points, plot the topography of New Jersey, chart your course through the woods, and with, you know, small recipes, they can then build on that and start doing professional grade work in very little time and with very little effort.
Yeah, and so unfortunately, I would say of these software, ArcGIS is the least amenable to this. It's not script-based, it's not text-based, it's clicking in Windows and not necessarily intuitive. So what we do here is literally provide recipe sheets that navigate students window by window, click by click, through a set of a few most important operations that we consider crucial to their future research in Cyprus. So for example, in this case, we're telling them to open a specific part of ArcGIS called ArcCatalog. It's where all the files are collected. Navigate to your directory containing raybird.csv. That's a data file that I give the students containing the locations of all the various kilns and pottery dumps and so on and so forth in Cyprus. It teaches them how to create what's called, ArcGIS calls a feature class, basically a table that contains latitude, longitude, and elevation information, and then whatever additional observations there are. Color of potsherd, number of pieces of iron, number of tools, etc. Teaches them how to create that file from their, basically, Microsoft Excel spreadsheet. And then in the same pop-up window, it teaches them how to set the coordinate system based on what they already know about their data. In what frame of reference do their data exist, and how can that translate? So all of this, certainly to me at first, seemed completely non-intuitive. And so the student has a hard copy of these recipes so that they can follow through in class with us and go back to it and apply the same set of set of rules to their future data that they collect themselves, either from the web or in Cyprus. And then hopefully, as they become comfortable with this, they can then go beyond and start doing other things. So in this example, for example, here are the data sets they work with through the recipes. They're given an elevation model of Cyprus. On top of that, they overlay the polygonal boundaries of the previous kingdoms from a few thousand years ago. And then in this case, for example, they computed the mean elevation and the area of each polygon, and thus each kingdom, and started to wonder what was special about each kingdom. Were some kingdoms isolated to certain topographic ranges, certain roughnesses, etc., etc. So they get a feeling for what type of analyses they'll be doing later with their own data.
Okay, we also used a lot of hardware. This was mostly software. We mentioned GPS, the radar. So we'll give you a quick overview of what we did. And here the keys, we're giving people expensive and fragile equipment and lug it all the way to Cyprus and use it there. We must try it on campus first. So we designed a set of simple campus exercises with the help of our helpers. One of them, and this wasn't for Cyprus, but we have a relative gravimeter that is a very, very sensitive instrument that will tell you that the gravitational acceleration from this point to the point down the hall will be different by a measurable amount, typically some value, 1 part in a million of the overall acceleration. Geologists have been using this for 100 years to detect buried ore bodies, fault lines in the subsurface, sedimentary basins. You know, it's an ancient and venerable tool for exploration. Among the other things that you can do with it is you can find, even though it's a relative tool, you can find the absolute acceleration of gravity, which you all know to be about 9.8 meters per second square. And the way to do it is by taking the relative gravimeter up a tower, like Fine Hall. So 3 years in a row, we really annoyed the mathematicians because our student had so much fun staring down the little level bubble and the little readout of that very, very, very sensitive instrument. And every floor of Fine Hall, they measured the relative gravity starting from the basement. And that curve that you see there is the result of that. The unit is in milligal, which is 10 to the minus 5 meters per second, and the floors here are between 0 and the 12th floor. And so there you go. Then they learn how to fit a regression line through it, and the result of that is that you find, and this was the objective of their lab, is what is the gravitational acceleration? And then the side benefit is how high is Fine Tower from this measurement and then compare it with another crude way of measuring the height by sighting it and doing an angle measurement. And so all of our students now believe in the theory of gravity, and we no longer teach the alternative. Here's GPS. Nope, we're done.
So the other instrument that more and more kids will have already experienced on their phones or whatever before they even get here is GPS, which is an invaluable field instrument because you essentially, if you want to use GIS, you need to know where you are when you're making an observation. So as part of the very first proposal for this class, we bought enough GPSs so that every student is just their own GPS on the first day of class. They keep it, they're responsible for it, they can use it as much or as little as they want. Well, not quite as little, but to some extent. And to learn to use it, we define a very valuable experiment that's done on campus that will guide their interpretation of all future GPS data. So what is labeled here, you should recognize campus there, are control points, CP, and control line, CL. Each of these is a landmark that we walk around with the students and define that they are to resurvey with their GPS twice a day throughout the duration of the assignment, 1 or 2 weeks. And the idea is to understand the accuracy and precision of their GPS unit. Is there drift? Is it associated with meteorology? Is it weather dependent? Does it depend how many satellites the GPS can see? Does it depend on their proximity to a building or time of day? And so they collect a group of data. So for example, here's an example table where they have GPS H, that's their particular GPS, versus all data, where they've compiled all the data from all the students. And they look at the mean and standard deviation both in northing and easting for each control point. And you can see, for example, control point 1 is a much larger standard deviation, which this student attributed to the fact that it's right next to a building. That's actually right next to Geo Hall. And in fact, the entire southern sky, where 3 or 4 satellites at any one time are, was invisible. And so it had a harder time triangulating. Here's another example. In this case, what they're plotting is along the control line, the position in easting and northing of all the points from walking back and forth along that line on different days. And in some ways here they're attempting to both evaluate precision and accuracy. So how well does the GPS return to the same point, but also how well does their line match up with the line in Google Earth that's viewable because it's a road. The bus drivers were so unimpressed with us that I didn't realize there were buses going back and forth there to Firestone Library. But anyways, then they plotted that as a residual here in the histogram, showing basically how far away from their line are they at any one time. And you can see at least it looks roughly normally distributed, but they were dismayed that it was from -5 to 5. So the point is that these Garmins, they say some error on it, which is virtually meaningless. And what they need to know is at any one time when they take a point, say in Cyprus, where are they and how well do they know where they are? Okay, then next, this was actually, well, for many of these things, we defined these projects as much as for our own good as for the students' good. But what we found after 2 years in Cyprus was that we had a hard time interpreting the radar and the magnetometry and the electrical resistivity because there was no control experiment. So this year, both for training for the students and for our own control experiment, we worked with the grounds crew on campus to identify an area over across near West Windsor where we could dig a big hole. They helped us dig that hole by bringing large diggers and bulldozers.
9 in total.
What?
We dug 9 holes.
9 holes, yeah. Then we filled those holes with objects of known size and density, mostly rocks. But in this case, I went to a local farm in Hopewell, and after they butchered 2 cows, and transported those cows in my car, and emptied those cows into the hole, and had the students look for them. So the students did not, so this was to approximate a tomb filled with bones. And
as you guessed.
and there's Frederik enjoying the sights and smells of the situation. And anyways, then we buried them. Yeah, the irony is that I do not eat meat, and I did all the transportation and procurement of this cow. So anyways, once buried, the students had to find them.
And so the tool that we have, one of them is the ground penetrating radar. This is Brittany. It's actually in Cyprus. It's mounted on a little card. The radar is the orange box, and 400 million times per second it sends a pulse down and listens for the return. So you can write as fast as you can, but you have to write very close and very well coupled to the ground. And the instrument is just essentially listening for the rate of return um, of what you send down, because the idea being that if there's something anomalously buried there, that it's going to send energy back at different rates than if there isn't, and at different with different amplitudes. So this is a very, very popular tool in utilities work, road building. One year we went and looked for underground tunnels on campus. This year we did the cow. We keep it fresh, except the cow, which was dead. And then, the whole thing of georeferencing this is keeping this on the right axis, defining the grid, not getting confused that you're actually running from lower left to upper right and plotting that and like knowing the right direction is part of the exercise. Similarly here, this is also a picture of Cyprus, but we did take it to the cow. This is our magnetometer. It has a GPS receiver sticking out of an antenna. The magnetometer is the white little thing which has, some atoms being brought into an excited state and falling back down, and the frequency with which their measurables change is a measure of what the strength of the magnetic field is. And so holding it very still and removing all metallic objects, people walk for days on end in rows upon rows upon rows, and then cross, and then walk some more, and then do it again, to map out with the resolution of maybe a meter spacing what the relative ups and downs are of the magnetic field. The magnetic field of the Earth, your compass, it's a gigantic number. It's like 50,000 nanoteslas. The variations on a daily scale due to storms in the ionosphere are, a few tens, and what they're measuring is a few hundreds of variations that are ultimately telling us about subsurface objects. That is the object. So this is the result in West Windsor, and with a little liberty, because we were using the handheld Garmins, and as Adam just showed, this is accurate to within maybe 5 or so meters. When we were in Cyprus, we actually used differential GPS, which is accurate to maybe 5 to 10 centimeters. So with a little squinting, and here the walk lines are there, the interpolation, all of which was done by the students using the little MATLAB scripts, and they pinpointed that blue area there of anomalously low magnetic field, which also coincided with a disturbance seen in the ground penetrating radar as the location of the cow. Ironically, it's not the cow they found, but more the act of disturbing the soil and us having dug a hole there, which is how most crime scenes are finding their bodies, not because they see the bones, but because they see the disturbance from the digging. So dig carefully if you must. Okay. Unbeknownst to me, Adam is very media savvy, and I was instructing, and the camera crew showed up. We are teaching the students how to use geophysical field techniques of a variety of types. The two instruments that we have taken out here are a magnetometer and a ground penetrating radar. The students are collecting data as they would in the field. They're setting up a grid, they're having everything GPS tagged, they're going with tape measures to try and define the physical grid as well as they can, and then as soon as they have these organizational matters out of the way, they're starting to measure.
This class is designed to give us an introduction to geoscience and its practical applications, because in our field trip to Cyprus, we'll actually be using all the tools that we've started to learn, including MATLAB, LaTeX, a lot of software programming that helps us analyze the data we collect from GPSs and different field instruments.
We go to Cyprus and we collect geological data and geophysical data, both on the island of Cyprus and at a specific archaeological site.
The most interesting part of the course is probably like field work and like actually getting hands-on with all these different material like resources that I've never used before, getting the experience with how to research.
I really like being out in the field and actually taking real data instead of having to use other people's data.
We're also learning how to use software,
Yeah,
which is a big portion of the class.
How to use LaTeX and ArcGIS.
They're collecting hundreds and thousands of data points today, which, of course, the big work starts after they're done, which is when they download all the data onto their computer and use a variety of computational techniques to look through it.
So anyways, after all of this hard work, the course culminates in student presentations, where there are groups that have done now nearly a half a semester worth of research in Cyprus, collected all of their own original data and analyzed it using the tools we developed and taught during the first half of the class. They present 20-minute presentations as groups. We invite as many people as we know on campus. Some of them come. It's usually...
I had a conflict. I told you.
It wasn't specific.
I'm joking.
Anyways, it's usually super fun, and I don't know if you agree with this, but the thing that I always leave this from is that the students are capable of way more than most people are willing to accept, and that I think
Less than they think,
Less
more
than
than we think.
yeah. No, well, I don't even know about that. I think the students are usually surprised at how much they learn, and I think that everyone on campus could benefit a little bit from that, than less teaching down to students and really challenging them a bit. They may work harder than they were hoping to, but hopefully they get more out of it.
I want before you go to your last slide, and then we'll take some questions. There's a couple of unsung heroes that are helping us with our class. We have a variety of TAs, and Alain was one of those taking, as you've seen in the video. There's also the librarians, because we send our students out to do their original research, and very often they end up in the library asking for data sets, ArcGIS files, old or new maps, and the go ask a librarian is, we have software, we have hardware, we also have Bertha and Louise and Yili all helping out, probably forgetting some. They make it into the acknowledgments of their papers, and let the word be out that we're very happy with it.
Anyways, then I'll
Take the next class.
We continue to try to innovate and do new things. So Frederik is taking next year off. So in the meantime, we're going to try to design a new course together with Amanda Irwin-Wilkins, who's the head of the writing program. And it's trying to be a bridge between courses like the freshman seminars and the writing seminar, and before junior papers, so that students learn how to actually write scientific papers using all the same or different sets of tools. So in this case, we're going to focus on data collected by drones. So the students will learn to fly drones, collect topographic and color data from the surface, classify that data, map out geological, geophysical, and human structures. In this case, what's pictured there is a shoreline from Lake Bonneville, which was the larger version of Great Salt Lake. During the last ice age, it was much wetter, and it turns out by understanding those shorelines, we can figure out how much wetter it was and what the last glacial climate was like. And then we'll get back at it and try to figure out a new freshman seminar.
And Marcel, there's still one spot.
Good to know.
So we'll be happy to take some questions if you have any.
I do. So the research that they do on like Alexander's path and all of that, that's a separate paper that they write. And where do they come up with the ideas for that?
They have 3 different writing assignments that they can choose to build. We suggest that they build so that it's one topic that gets bigger and bigger and bigger. But some find that their first hypothesis is untenable or not that interesting and will switch. And it's chosen by the student. Yeah. We tell them the fundamental thing that we give them feedback on is they have to be able to define a hypothesis that's testable. And that, I think, is one of the things they find the most challenging, because it's easy to come up with an interesting idea, but can they test it with data they can find online?
So the three, if I can just the 3 titles of their papers leading to the third and final one is, pick a topic in climate and topography.
Okay.
Civilization this time in topography. How is topography controlled or influencing civilization? The second one was add a mineral resource to it. How has a mineral resource such as silver in Greece or gold in Egypt in conjunction with topography defined the course of the civilization? And then the last one was climate, minerals, and topography and their influence on civilization. And by that time, most people have completely original ideas and have. Some of them are focused on China in the 6th century BC, and others are just jumping from place to place, and they're coming up with it themselves. And of course, we give them feedback from time.
The thing is, I think when the students have to find the topics themselves, it's both much more stressful and hard, but then it's their topic.
Right. But there is that guidance of topography and
Yeah.
and civilization.
So the first paper might have said, and illustrate it with one figure that you make in MATLAB using topography. And the next one would have said, and also add a figure in ArcGIS with a mineral resource on it. And the third one was a handful of figures with your own new data.
And so they're building throughout the semester, and when is the first paper due? Is it like a month into the course? Is it fairly
No,
evenly
it's like 2
distributed?
weeks. 2 weeks into the
Okay.
course.
Pretty,
So they're
The
very
2 week-
early on thinking about their topic.
The first one is 2 weeks in. I think the second one is right before fall break, and the third one is during reading period, Dean's Day. The third one, they kind of have to. It's a lot longer process. They have to write a proposal and a rough draft, and so those are both due before Christmas, and then they're done with their group research projects before Christmas, and they have basically reading period to write their final draft of their final paper.
and then we read with them individually about their paper, and then again about their draft, and then we have them read each other's paper in a round of peer review before they submit comments on the review and their revised version in their final draft. So the assignment is 5 parts to it,
So all 3 papers are separate from the field research.
Yep.
ideally.
Always now. We started
We have
out
been, yeah.
allowing when we did it in California, we allowed students to use some of the data collected as groups for their final papers, but it just wasn't as effective, I don't think. You know,
So what does the feedback look like in helping them pick good hypotheses?
Whether or not they can find good data and be capable of analyzing it. So there's a lot of good ideas, but if there aren't any good data, then you can't do it. And there may be a lot of good data, but you can't, if we suspect that they, don't have the tools yet, the questions are maybe too, multi-step. We want them to get something that they can do and see and conclude that nobody has ever done, seen, or concluded. And most of the time, that works very, very well.
Where do a lot of these different data come from? I mean, I know resources like maps and stuff we have.
Geological surveys, national governments.
NOAA, a lot of these students love
Like
to do their
climatology
climate
data
things.
is probably easy enough to find, right?
Mineral resource data is usually digitized from geologic maps.
Uh,
Topographic data is usually, in the U.S. it's state by state, and otherwise there's global data sets that.
So it's not hard to find.
Sometimes it
Well-
is, like Maricela dug up some arcane reference to somebody in, what was it, who had done some treeing of a piece of wood found in the Parthenon, and then gotta go find that.
And sometimes you have to digitize things,
Yeah.
which is tricky.
Yeah, it may not exist in digital form to be data.
How do you pick the places to go?
They picked us so far. California we went because there was a research station where people had been before, and so we at least knew where we would sleep at night. And Cyprus was because we started working with an archaeologist, Joanna Smith, who said, hey, I've been going to this place. I'm in need of some second pair of eyes and third pair of eyes, and then ultimately 15 pairs of eyes to help us with scoping out the future areas, and that became Cyprus.
But the key for all these places is to go places we've never been. And I think that's why we also limit it to a 3-year for each place, because by now, of course we haven't been everywhere in Cyprus, but we've been to a lot of the really nice spots, and we've not necessarily figured them out completely ourselves, but we have a lot better ideas, so the students don't see us trying to figure it out anymore. And it becomes a story rather than research.
So the year after next, you'll do a new location, but it'll be the same course. Is that
No, it may not be archaeological. It may
Okay.
depend. We'll use the tools that are required for wherever we're going.
Are there excavations being done or planned focused on some of the sites you identified?
Pending funding, yes.
And approval. I think getting approval from the European Union to actually excavate an archaeological site is a long process.
No, but Princeton owns a house on land owned by the Department of Antiquities in Cyprus.
So they don't have permission to excavate.
Not necessarily, but they will get that if they want. It's about money mostly in Cyprus.
Well, anyways.
So, depending on who you ask. But yeah, so there is now specific targets. And
Really thanks to the most recent group of students. Last year's students by then we were getting better with the instruments. It was an excellent group of students, and that was the most incredible buried wall or whatever that was.
And ultimately, the students figured out something very low-tech, which was that rather than covering a lot of ground with the ground-penetrating radar, you should focus on trying to penetrate the ground very well. So they packed the dirt, they divided the earth in squares, they focused on 10 by 10 grids rather than 100 by 100. And so they came up, this is Alain with Kathleen experimenting a little bit ahead of time. It's like, oh, suddenly they saw things. And like, okay, we have to revise our strategy of data acquisition, because knowing that that works, we'll do patches in places rather than large areas. And, you know, these are adaptations to the strategy based on something that, you know, an undergraduate and a helper found out, and then applied and taught the others to do.
So do the undergraduates start proposing modifications?
Well, so it was Alain, it was a postdoc, and Kathleen figuring out things in the day or two before the students would arrive on the site, because we knew that instrument was giving us some trouble, and like, let's try some new things. They tried it, and so yeah, they explained to us what we should be doing, and that worked very well.
But students do innovate. I mean, they're certainly evolved. The project I showed you with the tombs, where they were making measurements, I mean, it was their idea to measure the walls so that they'd have, because they were worried about spatially orienting the different measurements so they could reconstruct the dunes, you know. They're given leadership roles and have to figure it out. We become their field assistants when we're in the field.
How many you're limited to must be about 12 or 15 students or something like that.
Yes.
Although until last year or the year before, we didn't even used to fill up. So there's not usually that, I mean, this course is not filled. Our freshman seminar, I mean, last year we might have had 25 students apply, but it's not like there's way more popular courses. So these are not in high demand.
It's like a 24-hour commitment for 7 days and severe mental stress for 12 weeks.
27-hour commitment.
Right, field trip is not necessarily always a selling point to them, right?
Well, I mean, everyone always talks about, the humanities trips to Greece, where there's lots of nice, you know, vistas and things to look at and wine.
I've
and
never
we
been
have
on one of those.
not a drop of wine, a dirt road to be on, and 9 hours in the field followed by 5 hours behind a computer. It's hard. I wish it was more pleasant.
But it sounds like it's very
But going to
rewarding,
like the
but yeah.
Uffizi in Florence, you know, that's pleasant and useful.
Yeah, but they're not rewarded like these guys are.
But you know, being out in the dirt is tough.
And is it hot there that time of year?
It's hot. Yeah. It's hot.
Out when you're out in the sun and the baking.
Yeah.
And they don't shower every day.
I mean, it's. Oh, go ahead.
Sorry.
No, go ahead.
Okay. Yeah, from one paper to the next, do you see development in students dealing with some of the difficult aspects of doing science, such as dealing with uncertainties and identifying assumptions and things like that?
Yes.
On every level you can imagine, whether it's stating their hypothesis, making their case, referring to their figures properly, making figures that are usable, analyzing the data in a quantitative way rather than, I mean, we always joke, but almost always in the first topography one, people describe things like the red area of the map. You know, red is
The red
referring
area
to
on
an
the
elevation.
left.
Yeah, the red area on the left. And so, yeah, it's leaps and bounds usually on each assignment.
But so the thing is that of 12, 15 students, all of them put together know everything that it takes to be a scientist. They just don't know all of them, all of it. And so there's a lot of teaching that needs to happen from, you know, they figured out MATLAB and she figured out BibTeX before
And
the other person.
specifically in terms of uncertainties and such?
Well, you know, it's that exercise with the GPS is a very hands-on uncertainty thing. I'm sure that was new to people. It's not a, yeah.
I think depends on the data set. So, you know, like for some of the ones you saw, for example, again, that Dune team, there was another team that was counting layers, Varv-like annual layers in a rock. And those are data sets that are somewhat conducive to estimating error. Same with GPS data. But, you know, some of these data sets that they get online, they didn't collect it. They can't evaluate the errors necessarily themselves. They can compute an error in correlation if they're doing something like that. But otherwise, they're basically stating the error that someone else told them was associated with the data. So it's not always easy to propagate these uncertainty. I don't know how advanced that we ever get that.
Yeah.
So each student writes an individual paper. So is it common for them to turn this into a senior thesis or something like that?
One, I wouldn't say common. I think
They're
we could count a
freshmen,
few.
right? So we're 3 years later. I'm not sure.
We had one student. Do you remember Tim Keeler?
Yeah.
He wrote his music senior thesis based on the work he did in his freshman seminar because he did Markov chain analysis of layer counting.
That's a stretch.
So what does he?
So he was trying. His thesis question was whether or not, I don't remember which piece he chose, some classical music piece. He said, "Can I analyze this using Markov chain analysis, looking for patterns, and then randomly construct good music?" And it's like the Music Genome Project is not that far off from that. This was before that. That was way back, like 5 or 6 years ago.
But
I don't know.
that is uncommon.
Yeah.
I mean, they would have to then maintain an interest and ultimately major in an area that they learn something. I think all of them learn something that they'll hopefully be using at some point for their thesis. But topic-wise, it's not as direct.
Yeah, that's true. Because since you've taught this for so long, what's the distribution of majors, of like final majors?
That's
Up and
also
down.
changed. Well, it's also, I think it's been almost linearly changed. When we first started this class,
Count.
huh? Well, then two answers to that question. One is how many geo majors do we make? That has definitely decreased. We used to brag that we were responsible for half the majors in our department, which meant 5 out of 10. And now we're like 3, this year 19. 3 out of 19. Last year we were 2 out of 10 or something like that. So it's not that many. Maybe we're 1 to 3 per year out of our 12 to 15 students. But then in terms of what majors they end up, when we first started this class, by far it was mostly humanities-minded students looking for an STL. And then I think as the word got out that it was hard, this year was almost entirely the opposite. We were engineers and scientists or science-minded humanities people. And virtually no one identified themselves as someone who was trying to get an STL. I don't think there'll be a single...
That's a shame. Yeah, it would be nice.
Yeah. Would you say, is there a single person in our class that would be their only STL? I don't think so. Maybe one other. I mean, not many. I bet everyone will take another STL.
Everyone, yeah. And I mean, it's a crime rate, too.
No, you don't have to take another STL.
Oh, that's true, that's true, yeah.
Yeah. You only have to
I
take
think
one
everyone was
STL,
there.
but 2 ST courses.
What's an STL?
STL is science and technology course with lab, a general education requirement. And then there's also STNs, which are science and technology courses with lab.
But so it's not a course to fulfill rapidly a requirement. It's an actual thing that we hope leads to what it may. And certainly not rapid because it's very labor intensive to do all of that.
Right. Well, eventually we want like all STL courses, right? Should be.
Well, yeah. I
rigorous.
mean, we can only speak for ourselves.
So that's the end goal.
I don't think, if I had to guess, that we've been particularly successful at getting students who wouldn't otherwise have taken another STL to take another one.
Right.
I don't think we've succeeded in that. It's hard to know.
Right.
But I wouldn't, it's not obvious. We don't have students pouring in saying, I never would have taken another science class, but because of this we are. And we don't really get that feedback.
So it seems like it's shifted. Like now, it's also you're also providing this fabulous foundation for the students that are going on.
Well, that's what we hope.
Instead.
I mean, I feel like there's very few courses that are research oriented, so when they do get to their
At the
JP,
freshman level, at least.
or sophomore, or junior, I mean, they're really, I don't think
Junior
they're...
papers, right?
Well, yeah, but those aren't
It's
classes.
not a course, yeah.
I'll be honest, I came in with Woodrow Wilson, and I still have that mindset, but I looked at it and I was like, oh, this is really cool, I'm learning this, and I'll get a trip. I took the class, I ended up taking like 2 post classes, I continued the project, and I actually started building what we were looking at in 3D. I'm starting to work with like data analysis to see concentration of big businesses for my job, using QGIS, ArcGIS. And like, so I was definitely pushed into something I didn't really know existed. So yes, you
One.
do.
We got one.
One.